Welcome to part 1 of this Introduction to Statistics on Measuring Data. Let's jump right in. Let's start with a problem. Say you want to know how tall are Sasquatches. Well, the most exhaustive way to answer this question would be to go out and measure them all. But you can't do that. You can't measure the Sasquatch population in its entirety, given how elusive they are, because you'd never know if you'd ever measure them all. So you do some research instead. And the most authoritative figure you find on the subject is 8 foot even, which came from Woodland Pete in 1908 in an editorial to the Medford Mail Tribune. But not just to trust his authority on this, you do some more digging, and you find that the last 10 random sightings actually give a mean of 7.5 feet. So we have conflicting numbers here. So what do? Well, our question becomes, is that latest sample data enough evidence to reject and revise Woodland Pete's claim? This is a perfect example, if I say so, of the type of problem that statistics allows us to solve. It helps us get strong conclusions out of partial knowledge. That is, answering whether we should defer to Woodland Pete's authority or revise it will depend on analyzing a sample, which is, of course, partial knowledge of a population. This question is going to animate our series. So first things first, let's take a look at the raw sample data that you found. So in this form, this is a table of just facts about random individuals. So for our question, this isn't useful yet because we want to know a fact about the population. So we need to decide on a summary measure that is a descriptive statistic which will capture what we want to know, the fact of the population's average height. But before we go ahead and start crunching numbers, it's important to consider for a second which measure of data we ought to use. That is, how can we best translate what it is we want to know about a population into a number? We've said we want to know the average height of a Sasquatch, but by average, what do we mean? We should be aware that there are multiple measures of average. We've implied that we're using the most familiar of these, average meaning the arithmetic mean, where you add up all the values and divide by their count. But there are other averages, meaning measures of central tendency. We mentioned the mean. There's also the median, which if you order all the values by magnitude, you just choose the center. There's, of course, proportion, which is actually just the mean of binary data, a data set that's all ones and zeros. And there are others, the mode, or the most repetitive number, the geometric mean, which involves the square root of the product of all the values. The important point to note here is to be aware that we're making a decision on how we're going to mathematically model the fact of the population that we want to find out. And we should know that each of these measures of central tendency comes with a possible bias. Arithmetic mean, for instance, can be greatly affected by outliers, more affected than, say, a median would be. But arithmetic mean comes with great advantages, namely easy mathematical manipulation. So back to our problem. You know that you don't have access to the objective fact you're trying to measure. That is, you can't measure the true population height because you can't measure the whole population. The upshot is you're stuck with your sample. You only have your sample data to work with. So how does sampling data behave? That is, how accurately can it reflect its population? So focusing on how accurately the sample mean can mirror the population mean, we already know a couple things intuitively. First, that if your sample is big enough, its mean will be pretty close to the true mean. That when it comes to trying to estimate something, more data is better than less. Second, we already know that a sample should be random. A non-random sample risks bias. It won't be representative of its population because, for example, it could be accidentally oversampling from a relatively short Sasquatch family, biasing the population's mean estimate. So sampling can be more or less accurate depending on these. But let's ask a simple question we haven't yet. Remember that Woodland Pete's estimate for the mean height was 8 feet. Well, the sample data gave a mean height of 7.5. Doesn't that difference alone prove that one of these numbers is wrong? Well, let's consider the case of flipping a coin 100 times. We'd expect to get 50 heads and 50 tails, but what if we got 52 tails? This doesn't prove that it's biased. And why is that? It's because there's random variation, two possible outcomes, that is, not just one out of a fair coin, which can give rise to sample error. We wouldn't expect to always, or even probably, get exactly 50 tails out of 100 flips because of that. But what about 60 or 75 tails? The larger the difference between the observed result and the expected, the more suspicious we are that it wouldn't be a fair coin. But to prove bias conclusively, that is, mathematically, we need a precise measure of just how likely 60 or 75 tails is. Then, if it's so improbable for a fair coin to give this sample result, we'd reject the idea that's a fair coin after all. But the important thing to note for now is, when you observe a difference between an assumed population mean and a sample mean, that difference alone is not yet enough to say one of them is wrong. You also need to have a measure of the variation in the population data, because this variation, that is, the possibility of multiple outcomes, is what can create inaccuracy or error in the sample's mean. Let's pause on this term. What do I mean by error? Error is the fact that when you're sampling from a population, the sample's mean is usually not exactly equal to the population's true mean. Consider if you were sampling from a population with no variation, that is, one that had only one possible outcome. For instance, if all Sasquatches are exactly 8 feet tall, the population mean is 8 feet, and then any sample of any size that you were to take from this population could only be exactly 8 feet too. There'd be no error in the sample mean. But as soon as a population varies, as soon as there's more than one possible height for a Sasquatch to have, the sample mean might not match up exactly to the population's true mean. Error is introduced. Again, data with variation creates error in the sample mean, and more variation means more error. Let's think about this. Let's assume the mean height of Sasquatches is 8 feet. In a case with little variation, let's say 95% of Sasquatches are between 7.9 and 8.1 feet tall, all very close to the mean of 8. Then, if we obtained a sample mean of 7.5, it's odd, because this is way outside of the natural variation in heights and seems like a bigger difference than the sampling error could explain alone. On the other hand, in a case with large variation in heights, say 95% of Sasquatches are between 6 and 10 feet tall, the mean is still 8, but observing a sample mean of 7.5 is still less. It's the same difference, but the greater range of values inherent in the Sasquatch population makes sampling a mean of 7.5 unremarkable. In this case, it's just more likely sampling error is responsible for the difference. So now we need to know how to measure the variation in Sasquatch heights. That is, what's the average we should use here to measure the spread of the Sasquatch population's heights around their mean? Because since, again, data with variation creates error in the sample mean, we want to use this measure of data variation to calculate how much error is likely for a sample mean. This variation, or multiple outcomes in data we've been talking about, has a formal name: variance. Variance measures the spread of data around its mean, and it's very important in understanding statistics, so make sure you feel you have a good understanding of this slide before moving on. Variance is the measure we use to model the spread of data around its mean. It's the average we use to capture how spread out the data is with one number. Why is it important? When we can measure data's spread, we can ultimately infer the amount of error to expect in the means of samples taken from that data. We saw on the previous slide how, under the same assumed population mean of 8 feet, getting a new sample mean of 7.5 could either be unremarkable or extremely unlikely, all depending on the variance that was inherent in the Sasquatch population's heights. It all depends on the amount of variance. So there are actually two formulas for variance, one for population data and one for sample data. Let's break down what's going on in these formulas. First, let's look at what's the same between the two. Looking at the numerator, the first thing you need is x bar. That's the mean of the data set. So to calculate the numerator, you use every individual data point, that's I, from 1 to however many data points there are. You subtract off the mean to find the difference between that data point's value and the mean value, and then you square it and you sum them all up. So let's pause here. You might be wondering, why does variance use the squared differences between each data point and the data's mean? Well, foremost, we use it for easier math down the line. But we can also note it keeps all values positive so they don't cancel out. That is, values above the mean that would give a positive difference here don't cancel out with values below the mean, which would give a negative difference if you didn't square them. Finally, we can note that, for better or for worse, using squared differences to calculate variance has the consequence that outliers are going to be weighted exponentially. The second thing to note about variance is the averaging. So because the numerator first sums up all of these squared differences and then divides it by n, or n minus 1, we're getting an average. So variance is really the average squared difference the data displays around its mean. Now, what makes these two formulas different? The first thing to note is the different symbols. Population variance is notated by sigma squared and sample variance by s squared. They're both squared because they're the average squared difference of the data around its mean. But because we always need to be careful if we're talking about a population or we're talking about a sample, that is, we want to state a fact about a whole or state a fact about a partial bit of it, we use these different symbols to keep those two ideas separate. The second difference to note is the different denominators. Population variance finds its average by dividing by n, like you'd expect, but sample variance divides by n minus 1. Why? Remember that in our example, we can't calculate the Sasquatch population's mean height because we couldn't measure every Sasquatch. The population variance is similarly inaccessible, unmeasurable, when we can't measure every member. So when we can't know the population's variance, again, the best we can do is to try to estimate it from what's observed in the sample. And for mathematical reasons, using n minus 1, called Bessel's correction, will give a better estimate of the population's variance when estimating it from a sample. Finally, as a note for the mathematically minded out there, as you go further in statistics, note that you'll eventually see more consequences from, 1, the use of s squared as an estimate for sigma squared, especially at low n, or sample size, and 2, from the fact that variance itself is an estimate calculated from another estimate, that is, the mean, which is an estimate of the population center. You might have already heard of standard deviation, which is another measure of the spread of data around its mean, but this time in unsquared units, that is, on the same scale as the data itself. Standard deviation is simply the square root of variance. Again, keeping population and sample separate, here are the formulas. Because it's on the same scale as the data, this means that we most often use standard deviation when we want a number to summarize the spread of a data set. But you can see how easy it is to go back and forth between standard deviation and variance just by squaring and unsquaring. Mathematically, one important thing to note is that if you need to manipulate standard deviations, such as add two of them together, you'll need to go through variance. That is, you'll need to square the standard deviations into variances, sum them, and then take the square root of that sum. Now that we understand variance and standard deviation a little more, let's revisit our sample data. In the first column, we have the original 10 observations, and remeasuring the center of our sample, we get a sample mean x bar of 7.54 feet. Now, let's measure the variance in our sample. Here's the formula for sample variance again, and in the second column, we have each individual data point's squared difference from the mean. For example, this observation, 7.6 feet, minus the sample mean x bar, 7.54 feet, squared gives you this figure. Now, the average of all of these squared differences, the n-1 average, because this is a sample variance we're calculating, gives you 0.3849 feet squared, the sample variance being a squared figure. From here, it's easy to calculate sample standard deviation just by taking the square root of this, which gives 0.6204 feet. Now, how do we interpret this number? Well, sample standard deviation means that this is the average number of feet away Sasquatches are from their mean height, according to this sample. Let's summarize all of our population and sample data. So here's what we know about the population, which is actually nothing. But we're deferring to Woodland Pete's authority and assuming, until it's proven otherwise, that the true population mean is 8 foot even, like he said. Note that the population mean is denoted by the Greek symbol mu. But here are all the measures of our sample. So we have the mean, variance, standard deviation, and count. Note that standard deviation and variance are taken out to so many decimals because if we were to use this in an equation somewhere, any intermediate rounding we do now could throw off the final answers calculated from these. Here's how you can quickly calculate sample statistics like these on the statmagic app. In the descriptive stats calculator, make sure the toggle is on S mode to calculate stats for sample data. Sigma mode is for those rare cases where you have complete population data. Then, enter the 10 data points, choose your desired final answer rounding, 4 is fine, and hit Calc. You can then browse the output pages or lower the keypad to see all the results at once. So here are the key points I hope to convey in this first part of our introduction to statistics. First, that when we can't measure a population completely, like we can't measure the whole population of Sasquatches, we can then only measure it using a random sample. But sample data can only estimate the population's true parameters. We can only get estimates of the true mean and the true variance and standard deviation within the population. So the fact that we have to sample has an important consequence when it comes to estimating the true mean of a population. First, when a population has variance, this introduces error or inaccuracy into the means of the samples taken from it. Therefore, if you see a difference between an assumed population mean and the sample mean, like we did in our example, this could just be due to the error in sample estimation. So this difference in itself does not prove the original assumption wrong, unless the magnitude of this difference is larger than the error that is likely explained by the variance in the population data alone. From here, we want to know, how can we calculate the expected error that we get when sampling? That is, when using a sample mean to estimate the true mean. In other words, how can we calculate an expected range of means we're likely to see in a random sample, given that the population we're sampling from has variance? We want to know so that we can tell if a mean is or isn't likely due to just sampling error. To estimate this likely range of means, we'll first decide how to model our population. At this point, we turn from measuring data towards making more data modeling decisions. Just like we had to decide which average we should use to model the central tendency of Sasquatch heights, we'll now decide how to model the population as a whole. We'll use A, whatever is already known or assumed about the population, plus B, stats gained from our random sample, which we'll use to fill in any missing population assumptions. So what model should we use to model the heights of Sasquatches? Check out part 2 to see.